Hello and welcome to this video about resistance. We're going to look at what resistance is and what Ohm's law is, what factors affect resistance, and what are superconductors. Resistance is basically the opposition to the flow of current in a conductor. That kind of makes sense. It's the resistance, right? The flow of current is being resisted or opposed. Mathematically, it looks like this. We represent resistance with a capital R, and resistance equals the potential difference divided by the current. The SI unit for resistance is the ohm, and the ohm is represented by the capital omega, Greek letter. If you write it out by hand, this is an acceptable way to write that out. For many materials, including most metals, it's shown that the resistance is constant over a wide range of potential differences. So remember, resistance equals our change in potential divided by current, and that is equal to a constant for many, many materials. It's named Ohm's Law. Mathematically, it looks like this, and it's named after Georg Simon Ohm, who was the first to conduct a systematic study of electrical resistance. It's common practice to express Ohm's law as delta V equals IR. It's an easy way to remember it, or VER, if you can remember that. Ohm's law is not a fundamental law of nature, like the conservation of mass or gravity or anything like that. Some materials follow Ohm's law and some do not. Materials that follow Ohm's law are called ohmic, and those that do not are non-ohmic materials. We can see two different materials whose potential difference versus current is graphed right here. And you know that the slope here is going to be rise over run, so we have the change in potential difference over the current, therefore that should be a constant. We can see that the relationship is linear for this material. This is an ohmic material. This material does not have a linear relationship between the potential difference and the current. It is non-ohmic. So remember that electrons do not move in nice little straight line paths through a conductor. They're instead having repeated collisions with the metal atoms, and those collisions are going to behave like a force of internal friction. This is the very beginning of a material's resistance. So any factor that would affect the number of collisions is also going to affect a material's resistance. Some of these factors are listed in this chart. The length of a conductor affects its resistance. The longer something is, the more resistance it's going to have. You can see that right here. If we look at a cross-sectional area and slice our conductor down some cross-section, the area or thickness of that cross-sectional part of our conductor is going to affect the resistance. The more area or the thicker it is, it will have less resistance. So in our example, this one has lower resistance than this one. The type of material obviously affects the resistance. Copper has less resistance than aluminum. It just depends on the material itself. And temperature definitely affects resistance. Less resistance will be met if the temperature is lower. And that conversely would be true. Greater molecular motion or higher temperature is going to tend to increase the resistance. So, some practical applications. A resistor is simply a device that is used to control the amount of current in a conductor. And here is a picture showing a whole bunch of resistors on a circuit board. And the color, the different colors in the bands of these resistors represent a code for values of resistances. Let's do a problem together. The resistance of a steam iron is 19.0 ohms. What's the current in the iron when it is connected across a potential difference of 120 volts? I'm going to write down what I know. I'm given the resistance is 19.0 ohms. I know my potential difference is 120 volts. And I'm looking to find my current. I'm going to use my modified version of Ohm's Law. My potential difference, V equals IR. Plug values in, and everything's in the correct units, volts, ohms. My current is going to be in amperes, 6.32 amperes. So what about resistance and the human body? The human body's resistance to current is about 500,000 ohms when the skin is dry. But when the skin is wet, the body's resistance decreases. If the body's soaked with salt water, the resistance decreases even more. It can be as low as 100 ohms. That's because ions in salt water readily conduct electric charge. If a person's resistance is this low, it can be dangerous if a large potential difference is applied between parts of the body, because you know that current increases when resistance decreases. Usually, current in the body that's less than 0.01 amps will be imperceptible, or it might give you just a slight tingling feeling. Greater than 0.01 amps, currents can become painful. They could disturb your breathing. They could even be fatal. Also, perspiration contains a lot of ions and salts that conduct electric charge. You know that perspiration increases if a person's nervous or stressed or working really hard. This also decreases the resistance in the human body. And last, let's take a look at superconductors. What is a superconductor? A superconductor is a material that has zero resistance below a particular temperature, and we call that temperature the critical temperature. There are thousands of known superconductors. Aluminum, tin, lead, zinc are some of them. And below, here's our critical temperature right here. A superconductor below this temperature will have zero resistance. If this is zero resistance when the temperature is colder than that and lower than that. Here would just be a normal metal, and the amount of resistance, how that affects a normal metal. And one last interesting thing to note. We're going to talk more about magnets in the next unit, but electric currents do produce magnetic effects, and this is a picture showing the interaction between a current in the superconductor. Right here is the superconductor being cooled by liquid nitrogen, and it's interacting with this permanent magnet right here, a small permanent magnet, and causing it to levitate or float above the superconductor. It's called the Meissner effect. Magnetic levitation has been used to design passenger trains. Here's one on a test track in Germany. Advanced ideas, try the conceptual challenge on page 704 of your textbook. Maybe you'd like to look into the use of these magnetic levitation passenger trains. Where else are they used in the world? How much are they used right now? Or any other questions you have about any of the things in the video. I look forward to seeing what you come up with, and we'll see you in class.